All right. Mine obviously does not look like your foldable up here, guys, but under the solid section, you should be writing it in. What I have here, so you're on the very back of your foldable, the very, very back, where it says solid, liquid, and gas. You'll notice that each one has a box up there at the top. Guys, in that box, we're going to draw particle diagrams, all right, as to what these states of matter look like. Solids, what can you guys tell me about solids? Close together, right? So if we're going to draw our particles in that box, how are we going to draw them? Close together. And very, very compact. And what kind of arrangement? Random, organized. Very, very organized. So, something kind of like this. Very close together, the particles. Very, very neat in rows and orderly. All right, something like that. All right, you get the idea of what a solid is. And we've done it with our hands before where they're moving. They're kind of vibrating slowly back and forth. All right, but they are in motion. There's only one point where they're not in motion. When is that? Absolute zero, which is zero on what scale? The Kelvin scale. Zero on the Celsius scale is what? Freezing. It's when water freezes, not just everything, but just water. All right, so what holds solids together? Something we talked about in our last unit, actually. Intermolecular forces, guys. So we've got an attractive force, IMFs. Anybody remember what our three IMFs are that we talked about? Dipole, dipole, hydrogen bonding, and the other one? London dispersion forces. We'll come back and talk more about those at some point in the future. All right? But it's the attractive force, guys, that holds solids in a fixed position. The key word is what there, do you think? Fixed. All right, that is our key word. So you should highlight that. All right, fixed position. That's our key word. There are two types of solids that you guys were to look at. What's one of those types? A crystalline, right? So we've got a crystalline solid. What can you tell me about crystalline solids? What's that? Very rigid. Mary, what'd you say? Geometric, right? So remember the video last week that we watched? There was that one guy. He was kind of in this room with all these crystals. He was talking about how amazing they are and whatnot. But he said one thing that's very interesting, guys, with quartz. Whether you have quartz in Arkansas or quartz in Brazil, the angles were the same. So they're very, very, very organized in structure. So crystalline structures, guys, they're very organized. And they have a repeating pattern. All right? Organized, repeating pattern. So that's one type of solid. That's the organized, very rigid, structured one. Then we've got another solid, which is called what? Amorphous. An amorphous solid. What can you tell me about an amorphous solid? It's what? All right, supercooled liquid that acts like a solid. But what else? In more general than just that specific. No true melting point. That's a property of it. But be less specific. You guys are absolutely right with what you're saying. But very, very, there it is, guys. That's the key that I'm looking for. They're random, all over the place, very chaotic. Is that what you said, Mary? Sorry, did not hear that all the way up here. So they are arranged very, very randomly. All right, meaning they have no organized structure. So some examples, the classic examples that we have would include what? Glass is the best example. It's a super, super cooled liquid. It's actually a fluid. If you look, guys, at very old buildings, I'm talking like 100 years old or more, the windows at the bottom are actually wider than at the top because over time the glass will start to settle out and it moves slowly. It's the slowest moving fluid there is. And they actually get wider at the bottom and they get thinner at the top. Now I'm talking decades and decades. If you go home and look at your windows, it's not going to happen. All right? It's going to take years and years for that to happen, but glass is the classic example of an amorphous solid. Other ones include clay and some plastics. More of your soft plastics are the ones that are amorphous. What'd you say? Legos are amorphous? Why do you say that? Because you've melted them down before? I don't know if that's true, because that's a harder plastic. 4 things that I want you to remember with solids. You're going to keep that in your section of solids on your foldable. I need a new slide because I ran out of space. So, point 1, they have a definite shape and volume. Definite shape and volume. Point 2, they have a definite melting point. Amorphous solids would be the exception there. Right? They don't always have a definite melting point, but all other solids will have a definite one. Legos are still under, we're going to go into a little bit more research, all right?
I melted them down and they don't turn into liquid, they turn into putty because they're amorphous.
Really?
Yes.
That I actually want to try that. High density, guys. Solids have high density. What's our density formula? Right, D equals mass over volume, guys. So, their mass typically is a lot larger with less volume space. And point number 4 is that they have a low rate of diffusion. What does diffusion mean? Yeah, combine or mixing, right? Guys, solids can mix. Some can, not all of them. But it's a very, very low rate. And it typically is only at the surface. All right, I'm going to add that point in here. Only at the surface. And again, it's not all solids, some. All right, some solids. I don't know one off the top of my head. But going with what Ethan said with the solid the other day of cheese, I'm thinking cheese could diffuse at the solids, or at the surface of it. If you took 2 different cheeses. Yeah, American cheese is already diffused. Absolutely. Anyway, guys, moving on to the next one, which would be liquids. Let's talk about those for a minute. All right, so we've got our box at the top. How are liquid particles in comparison to solids? They're more spread apart, all right, but they're not super far apart. So we're going to draw like our water level in there. We're going to draw particles, guys, that are kind of a little bit more spread out. They're still fairly close together. This is when we did our hands. They kind of rolled around each other. They can flow or glide past each other. That's what fluidity means. Solids have had a definite shape and a definite volume. So I've got this bottle of water over here. When I move it around, does it have a definite shape? No. No matter how many times you move it, it's going to continuously change its shape. But what about the volume? It stays the same, guys. So they have a definite volume. They've got a definite volume, but an indefinite shape. That's something that I would have highlighted. Definite volume, indefinite shape. I would also go back to my solids and I would highlight these 4 points. Make sure you know those 4 points. So there are 4 points here we want to remember with liquids. Point number 1, they have a relatively high density. All right, relatively high. In comparison to gases, it's very high. Solids, guys, it's not as dense as solids. Right? Now that doesn't mean that there are that all liquids are less dense than some solids, because there are some solids that will actually float in a liquid. What's one example of that? Ice, guys. Ice is less dense than liquid water. Right? It really is due to the fact of how the particles are arranged, but regardless, solid ice, solid water is less dense than the liquid state. Number 2, they are relatively incompressible. Meaning they're pretty much as tightly packed as they can get. Solids, guys, they are incompressible. We didn't even need to add that in there because you can't get them kind of tighter packed than they already are. Gases are the only ones that are really compressible. You can see a significant difference in their volume when they're compressed. Number 3 for liquids, they have the ability to diffuse. Right? They can mix very easily. See it, and you do it all the time. Like in Arnold Palmer, right? Tea, lemonade, they diffuse together, they mix together. It's the only acceptable way to drink tea, in my opinion. Sweet tea, ugh. Regular tea, ugh. Mix a little lemonade with it, gets a little sweet. All right, I can deal with that. With a little bit more lemonade than tea, actually, in my opinion. Yeah. I don't like tea. I know. So the 4th point for liquids is that they have surface tension. What is surface tension?
It's the tension on the surface. It's like emotional tension. All right.
Not emotional tension. All right, it's at the surface. Shh. Right, and not actually bonds, guys. It's those intermolecular forces. It creates what we call a film. Hold on, not right now. It's a film that is created by intermolecular forces. All right, this allows, you've probably seen the bugs that can kind of skirt across the water. That's because of surface tension, guys. Tomorrow, when we do some mini labs, all right, you guys are actually going to get a paperclip to float on water, a piece of metal to float on water. All right, not right now. We need to get through this, and then I'll get your question. What? Really quick. You got like 10 seconds.
Isn't it like when you jump into a pool, like the surface of the water is more buoyant?
No, not buoyancy. Buoyancy is a little bit different. All right, moving on, guys, to gases. All right, so gases, guys, their particles are going to be more apart. I'm drawing arrows on them as well to show that they are in constant motion and they bounce off of container walls. All right. And off each other, absolutely. But they're in constant motion. That's why we're drawing arrows with the gases. All right, we've got this thing called an ideal gas. What is an ideal gas? Right. It's imaginary as well. That's the thing you've got to remember, guys. It's imaginary. All right? It's an imaginary gas that follows or fits all the assumptions of KMT. There are 5 points. What are those 5 points? Need to know them. What's that? Yeah, what are they? I'm asking, what are the 5? Shh, she raised her hand. Caroline, finish. All right, particles are far apart, and there's a lot of them. What's another point? Constant rapid motion. Elastic collision. What does elastic mean?
Bouncing.
Bounces off, meaning no kinetic energy loss. All right? 2 more. Temperature equals the average kinetic energy. And the last point, 1 second, I'll get your question. What's the last one, folks? You have your foldable. Look back at it. No forces of attraction or repulsion. Josh. No. It just means because they're in motion already, so potential energy means it's stationary, so there's no potential energy change. And we'll talk more about that when we get to heating and cooling curves tomorrow. All right. So, guys, real gases. A couple more things we're adding before the bell rings. Real gases behave most ideal when? At low pressure, high temperature. You want those moving as fast as possible and as far away as possible. And then lastly, gases have an indefinite shape and an indefinite volume. They fill whatever container they are placed in, whether it's a room, a gas cylinder, or whatever.